Good afternoon, everyone. Welcome to my first screencast for AP Chemistry. This screencast is going to be about colligative properties of solutions. So there are 4 colligative properties of solutions that we're going to discuss. One, vapor pressure reduction, but we've already discussed that in class, so I'm not going to discuss that on this screencast. I'm going to try to break the screencast up into 3 separate screencasts. We're going to talk about boiling point elevation, freezing point depression, and osmotic pressure. So we'll break this up in maybe 2 or 3 10-minute screencasts each. So the first thing we're going to talk about is boiling point elevation. So we know that a liquid will boil when the vapor pressure of the solution equals the atmospheric pressure. So at sea level, pure water will boil at 100 degrees Celsius. And that's the temperature when the vapor pressure of the water equals 1 atmosphere, because at sea level, the atmospheric pressure is 1 atm. Now, if we add a non-volatile solution, if we add a non-volatile solute to the pure water, the vapor pressure would decrease and the water would stop boiling at 100 degrees. So, in order to boil that solution with the non-volatile solute, now remember, non-volatile solute is something that's not going to go into vapor very easily. So your ions, like NaCl, that's a real typical non-volatile solute. In order for that solution to boil, we must increase the temperature. And by increasing the temperature, then that's going to cause the rate of evaporation to increase, which then therefore the vapor pressure will reach 1 atmosphere. And when that vapor reaches 1 atmosphere, the solution will boil. So the boiling point elevation can be calculated using a formula with the following variables. And I'm going to give you the variables first, and at the very end of this I'll give you the actual formula. So delta TB is the change in boiling point temperature between the solution and the pure solvent. Remember I, that's Van Hoff's factor, and again that's going to be dependent on the number of ions in solution. If it's a non-electrolyte as your solute, then I is going to equal 1. Now M is molality, so make sure the italicized M is, you're calculating it for molality. And then KB, K sub B, is the boiling point constant for the solvent. So the boiling point constant is something that you're going to look up in the book, or they're going to give it to you. Possibly you can calculate it if they give you all the other variables. But in this case, for the example that we're going to use next, the KB of the water is going to be 0.512 Kelvin times kilograms per mole. So up in blue, I wrote in what the Van Hoff factor is. Again, it's the number of ions in solution, or it equals 1 if the solute is a non-electrolyte. So down the bottom left in black ink, there's the boiling point elevation formula. The change in temperature equals I times molality times KB. So let's do an example of a boiling point elevation. Okay, so what is the boiling point elevation when 3.12 grams of NaCl is added to 0.65 liters of water? So first step, calculate molality. So we can calculate molality based on, there's the bell. We can calculate molality based on the number of grams of NaCl we have. We have 3.12 grams of NaCl, and we can divide it by the molar mass of NaCl, which is the 58.44 grams, to get 0.0534 moles of NaCl. Now, to calculate molality, we also need the kilograms, the mass of the solvent, and we have that because they gave us 0.65 liters of water, and you don't really need to do the calculation, but I did it for you just so that you can see where I'm getting the kilograms of water from. So we use the density of water. So 0.65 liters of water is going to equal 0.65 kilograms of water. Now we can use these two numbers here to calculate molarity. So that's moles of solute. Molality. We're calculating molality. So that's moles of solute divided by kilograms of solvent. And we take our numbers that we calculated, and we're going to get 0.082, and again, that's your molality. So, step 2, calculate the boiling point elevation. So now we have enough information to plug all of our numbers into our formula. The change in temperature equals I times molality times the Kb. And remember from the previous slide that the Kb of water was 0.512, I believe. So let's go to the next step. So now I is going to be 2 because when NaCl disassociates, you have 2 ions. Our molality is calculated at 0.082, and then our Kb of water is 0.512. Multiply those all together, and here you go, and there is your answer. Now, what that is that's a change in temperature. So, what we want to do is we want to find out, well, what is going to be the temperature of the solution for it to boil. So we know that pure water boils at 100 degrees Celsius. So the new boiling point of the solution is going to be 100 degrees 0.084 Celsius. So what I did is I just added the 100 degrees Celsius of pure water plus the 0.084 to calculate the new boiling point. Now, remember that the change in temperature in Kelvin is the same thing as the change in temperature in Celsius because the magnitude between Celsius and Kelvin are the same. So I'm going to stop right here for our first screencast of colligative properties for boiling point elevation. I'm going to come back and we'll have another screencast with the freezing point depression and osmotic pressure. So hopefully this will work out. And thank you for listening.